Alright, welcome back to the pycse channel. Today I'm going to look at how we can solve boundary value problems in Python. These are one of my least favorite problems to solve, so I was extremely pleased to find out that there is a solvebvp function in SciPy now that can help us solve these problems. So we'll look at this problem that I have highlighted here. This is the concentration profile inside a catalyst particle slab. And we have this differential equation, second order d squared c dx squared equals Thiele modulus squared c squared, and boundary conditions that at the center of the slab here we have no flux. So this solution is flat, and this is a dimensionless version of the equation. So out here at the surface of the slab, the concentration is normalized to be 1. And the goal here is to find c of x. And it's a boundary value problem because we have a differential equation that describes the behavior here, but we know one value at this boundary and one value at this boundary. So we cannot use solvebvp directly unless we would, say, guess what the value is and use like a shooting method. So we're going to take a little while to go through how we set up this equation in solvebvp. So this is now in scipy.integrate solvebvp, and let's take a look at how that is called. So over here we can see the signature. We have solvebvp. It's going to take a function that we'll look at, some boundary conditions, an x and a y, and those are the 3 or 4 main arguments that we have to provide. Okay. So let's look here. This function solves a first order system of ODEs subject to some boundary conditions. So we have a system of ODEs, dy dx is some function of x. We're going to ignore this parameter and ignore these features over here because we don't need them for this problem. But the function I'm showing you is quite a bit more useful than just solving this specific problem. Alright, let's see. So the function has to be callable. It's the right-hand side of the system. It looks like a function of x and y, and x and y are both going to be arrays that have a shape. We'll talk about what that shape is as we go. Then we need a boundary condition function that's also going to be taking the 2 arguments ya and yb. That is the solutions of y at the a boundary and the solutions of y at the b boundary. And we have to compute something that we're going to return as that will be 0 at the boundary conditions. And then x is going to be an array that we solve the boundary value on. And then y is going to be an initial guess for that function solution. So you can already see this is somewhat like solvebvp in the sense that we need functions to define the ODE, but it's also like fsolve or root because you also need a boundary condition function that's equal to 0 at the solution, and we need an initial guess for the solution. Okay, so what we need to do then is convert the second order equation into a system of first order equations, and then we have to derive some functions. So I'm going to switch to a different view so we can see how that's done. So let's check this out. Here I wrote down the equation that we were given. And normally what I do in a case like this is define C1 is equal to C, and then C1 prime is equal to C prime. And then we'll define C2 is equal to C1 prime, and that means C2 prime is equal to C double prime. And now we can plug these back into our equations and we get C1 prime is equal to C2, and C2 prime is equal to the Thiele modulus squared C1 squared. And then we have to adjust our boundary conditions. We have C1 prime of 0 is equal to 0, and C1 of 1 is equal to 0. Alright, so these are now our 2 new equations. These are the ODEs are here, and these are the boundary conditions. Alright, so those are the things that we want to be able to integrate into functions. So let me just copy this and get back to what we had over here. Alright, so let's put this in here so we can see it. Here we go. Let's see, maybe we can make this a little bit smaller. Alright, so that's what we have to work with. So let's go ahead and define the first set of functions for the ODEs. So I'm going to call it BVP, and this is going to take two arguments like this. We'll say C1 comma C2 is equal to C. So C here will be an array for the whole solution, and it has to have a row for C1 and a row for C2 that will represent the whole solution. Then we can write dC1 dx. That one up here is equal to C2, so we just write it directly. And then we have dC2 dx, and that one is up here is equal to, let's say, phi squared times C1 squared. And we should define what phi is. What did I say it is up here? Let phi equal 10. So phi is equal to 10. And then finally we need to return these two things. So we'll just return dC1 dx and dC2 dx. And I usually think it's a good idea to try to evaluate those, but we don't have the right things set up for x and c yet, so we'll skip that. Now for the boundary conditions, we're going to have to define another function, so I'll call it BC, and that's called as CA and CB are the two arguments. That is, what is the concentration or the solution of C1 and C2 at the boundary A, in this case x equals 0, and CB, which is the boundary where x is equal to 1. And so here for, I don't know, transparency or like making sure I remember what we're talking about, I almost always do this. Whether I'm going to use these or not, this reminds me that this is the solution of little c1 at the A boundary, and this is the solution of c2 at the A boundary. And this is the solution of C1 at the B boundary and the solution of C2 at the B boundary. And now we have two boundary conditions. We need C1 prime at 0 to be 0. And so that C1 prime is equal to C2. So this is actually equivalent to saying C2A is equal to 0. So let's return the first one. Let's just return C2A. And I'm going to make a note here that this is equivalent to C1 prime equals 0. C1 prime of 0. Alright, and then the second one is that C1 at 1 is equal to 0. So 1 is the B position over here, or the other boundary, so I need C1B to be the second thing that gets returned, and so we'll just return C1B here, and we need that value to be 1, so let's return minus 1 here. So now when we have the solution, C2A is going to be 0, and C1B minus 1 is going to be 0, and those are the two functions that we need for that. Alright, so let's go ahead and now figure out how do we make the X array and the Y array. So the X array is simple. Let's just import numpy and say X is equal to np.linspace from 0 to 1. This will make 50 points. The first value 0 is going to correspond to this boundary condition, and the last value 1 is going to correspond to the other one. Now, the tricky thing is, how do we get an estimate for Y? So Y is going to look roughly, the solution looks roughly like this. That is, it's going to go from 1 over here, and it's going to come down to some intermediate value here, and it has a slope of 0. So there are lots of ways to think about doing this. We know this value is 1, and we know the derivative here is 0. And a good question is, where from 0 to 1 do we get here? Now, here's where you have to use a little intuition or understanding of what's happening and how the telemodulus affects the concentration. So when the telemodulus is high, it means that the reaction rate is very fast compared to diffusion, and so the concentration is going to drop very quickly and level out over here, somewhere in this range. So we know, we could guess what a value here is. It's something low, non-zero, and it has to go up to this value there. All right, so let me come back down here and motivate what I'm going to do next. So the idea here is coming back to our picture. We have here's 0 and 1 on the x. We're going to guess a point here, and we have a 1 here, and we know this point. And we want some function that kind of goes like this. And any function will do as long as it has those properties. Now, we could try a straight line, and that does actually work. So it's really simple, but it has the wrong boundary condition down here. And so a reasonable question is, could we just pick some number, some value over here, and just fit a polynomial through it? And that's the approach that I'm going to take. So let's say we have, let's say this point is 0.1, this point is 1, 1, and let's do something in the middle here, 0.5, and we want this to be kind of flat, so let's say that this value here is 0.5. If it was up here, it would be 2 straight, so maybe we can cut the difference. So if this is 0.5, let's say 0.3. Okay, and what I'm going to do is just fit a quadratic polynomial through that, and then we'll see how it looks. Okay, so back to the idea. So we're going to say that parameters is np.polyfit, and polyfit takes some x data, so we have 0 and 0.5 and 1, and then we have some y data. The y data is 0.1, 0.3, and 1, and I want to fit a polynomial of order 2 through that. And then we're going to use np.polyval to get it. np.polyval, and we're going to fit the pars and evaluate it on x. All right, and now let's import matplotlib plot.plot x comma y and see what we get out of this. That looks pretty good. So somewhere it looks pretty flat here. It goes up to 1 and has all the right shape. So that's a pretty good initial guess. And then that's a guess actually for C1. And then to get C2, C2 is just going to be this times C1 squared. So if that's what C1 is, then let's say that C2, I guess I should call this one C1. And then C2 is just going to be phi squared times C1 squared. And let's also look at that one. Plot.plot x comma C2. And it goes up like that. So it's kind of off scale, but it's hard to tell what's going on. So finally we need to put those together and make our solution. So the solution then is solvebvp we take our BVP function, our boundary condition function, x, and we'll put C1 comma C2 like this. And this is our initial guess on y right here. And now if we run this, let's see, it says algorithm converged to the desired accuracy. That's usually good. And we have success is true, we have x and a y array. None of this is super nice to look at. So let's go ahead and plot it then. So we're going to plot sol.x. And we don't really care about C1 and C2 anymore. We really only need to know about C1. C2 is just a temporary variable. So sol.y, let's unpack them. C1 comma C2 equals sol.y. Then I can just put C1 here. And we have now the solution to our boundary value problem. And it goes up, and maybe we could plot our initial guess. Oh, I probably renamed it already. Here is the solution to the to that. Let me go back up, and maybe we can copy our initial guess right here. We'll evaluate it here. And you can see we were not super great. This was a little bit too high and the curvature is all wrong, but otherwise it's able to converge. And so that's what's happened with solvebvp. It just relaxes down to this space down here. And I guess maybe one final thing that's interesting to do with this is to integrate the area under this curve. That gives us something that is equivalent to an effectiveness factor. And a way to do that is that we can evaluate sol.sol at some number. So let's say here, this will evaluate this, and so we can write and integrate this with quad. So let's integrate that let's import quad. We'll define an integrand that is here, and then we'll just return, let's say, C1, C2 equals sol.sol of x. You do have to be a little bit careful with this dense solution because it's just an interpolator, and so if you don't have a high quality solution, then it's not going to work. And now we just integrate that from 0 to 1, and it will give us the effectiveness factor, which in this case is only, it looks like 0.08%. Seems like that's not right. No, I guess that's probably right. So only about 8% of the area up here is actually being used effectively, and the other 92% is not used effectively. So you would be well served by changing your catalyst geometry to decrease the TLE modulus to make things more effective. All right, so that's the end of what I wanted to go through today. Let's just review. We started out with this second order differential equation. We converted it to a system of first order differential equations. We had two boundary conditions. We derived those conditions here. We defined a function for the ODEs, another function that is 0 at the boundary conditions. These are the solutions of 1 and 2 at A, the solutions of 1 and 2 at B. Then we defined a grid that we solved the BVP on. And this was how I made an initial guess for it, and I just used some intuition about how we could take 3 points that are at the boundaries and an intermediate point, fit a polynomial through it, just to get an easy way of calculating this array for the solutions. And then finally, the second one is derived from the first one, since once you know the first one, we have an equation for the second one. And then we solve the BVP here, we shrink that, and then we plotted it here. And here I just show the, let's add a legend here. Let's see, we plot the solution, and then the initial guess. Alright, so that's it. As you can see, it's a little more involved than just to solve IVP, but when it works, it's remarkably flexible. And once you have the solution, here I didn't show the equation, but you integrate c squared over that interval, and that gives you what we call the effectiveness factor. And so we can go from this solution directly to the effectiveness factor and this estimated error. All right, that's it for today. Thanks for coming, and I will see you next time.